It's called Ants Roberts, or alternatively, is that old bugger still working? But Ants and I have been colleagues and they say the same about me. So Ants and I have been colleagues for over 30 years. And so very warm welcome, Ants. I'm still pleased to see you're upright, and we're looking forward to your talk.
I had a sleep before, so I'm right now. Great. So I am a soil scientist by training, and I worked for AgResearch for 22 years, and I've worked for Ravensdown for 21. Right. So I'm going to talk about science that I've been involved in, but I didn't actually do, which is a really good trick for a scientist, get someone else to do the work, take the credit. It's the two professors, Keith and Dee, who already did the work on the nitrification inhibitors in the earlier session this afternoon. I'm not sure whether you realise that they also are the scientists who developed and helped Ravensdown commercialise DCD, which you've heard came to a sticky end. And they were so hurt by that there's no more work in DCD, so their mind turned to effluent. Now, I said to effluent, not into effluent. I'm trying to keep you awake, all right? This is the last session. Okay, and so what they started doing was, the talk is actually concentrating on methane from livestock manure management, in particular dairy farm effluent manure management. Now, in the breakdown of agricultural gases in New Zealand, methane from livestock manure is about 4% of the total, but MPI tell us that of the dairy industry, 7% is in the dairy industry if you take the beef and sheep contribution out. So we're focusing on that. And so Keith and Dee, they work at Lincoln University in Canterbury. Water is important, water conservation and efficiency of use is important. They looked at treating farm dairy effluent to recycle water where they could, and so basically they put together sort of standard engineering techniques and chemicals from drinking water management around the world to develop a way of treating farm dairy effluent to clarify the effluent as it's washed out of the farm dairy into holding tanks. Iron sulfate compound is added to the effluent mixed with it, and it flocculates the solid material. So the solid material clumps together and then starts to drop out of the solution. Now, bear in mind that farm dairy effluent is about 3% solids, so it's taken out the solids. You can see a picture there. You can see the picture there of the clarified effluent. That's the solid in the bottom. It's not solid, it's still got a lot of liquid with it, but this water can be reused time and time again to wash down the farm dairy yards. It's called green water by the industry, and this is actually a lot safer than quite a lot of the other green water systems because they also found that over 99% of the fecal coliforms died during the clarification process. Okay, so there's the results from 3 pilot plant tests. You can see, yes, there is some data there, but it's so good that it hardly registers above 0, right? So it clarifies effluent very effectively. And they also found that by adding the polyferrous sulfate, it also reduced methane emissions from effluent storage ponds. And they tried it on a number of different effluent systems across, dairy effluent systems across New Zealand, and it worked very well. So over 90% of reduction in methane emissions from these effluent ponds. And they scaled it up to kind of farm system level, and it still works just as well, in this case 99.9%. All this stuff is published by these scientists. Right, so what's the mechanism? What's the mode of action? So it's a long time since I memorised the Krebs cycle, or the tricarbolic, the Krebs cycle, and so I'm not going to give you a biochemical lesson, but I'm just going to race through this. This is the cascade of methogenesis in anaerobic digestion. And And we can see that down here you get acetogenesis, and then methanogenesis is the final step. So, what does adding polyferrous sulfate to effluent do? Well, it feeds basically the iron-reducing bacteria, the sulfur-reducing bacteria. They go into competition with the methanogens for substrate, so they use the substrate that otherwise would be used by methanogens, but they also, and so they inhibit the growth of the methanogens, and they stop the process there because they're using up the substrate, but they also control the redox potential of the effluent. What does that mean? It means that that the methanogens basically keep the redox potential above that which methane, at which methane can be formed by the methanogens. So that's the sum total of my organic chemistry for you today. I will test you on it after though. So that's what it looks like. That's the dosing machine. It's a computer-controlled dosing system for effluent storage ponds. That's the Mark II version. And the Mark II version, which they're working on now, decreased methane from ponds by over 95%, kills 99% of the E. coli and the other fecal coliforms, and there's some co-benefits. One farmer is using a pilot plant on his farm in the... sorry? I wasn't talking about you yet, Stu, but I'm coming to you. Yeah, in Lake Ellesmere catchment, where phosphate leaching can be a problem on some of those soils and getting into water affecting water quality, and that farmer is using it because they've also found that it reduces the dissolved reactive phosphate in the effluent, and that reduces the leaching risk for phosphate. And also in tile-drained areas, we see that there's a lot less phosphate getting down into the tile drains where effluent is applied on the surface. And also it reduces ammonia volatilization. So there's a couple of co-benefits, but why I'm talking to you here is because of the effect on methane. What's the size of the prize? And so it's very late in the afternoon, so you will not challenge my maths. So in terms of the dairy system, there's about 14 million tonnes of methane from enteric fermentation, and about 1.4 million tonnes from the manure management on dairy farms, according to the inventory and what have you. If we can reduce those methane, and 90% of the methane emissions from the manure management category of dairy farms is from the effluent ponds. If we can reduce that by 90%, we can basically reduce the total methane emissions from the dairy industry by about 1.1 million tonnes of carbon dioxide equivalent, which is about 7.2% reduction. So to paraphrase one of the august speakers from the morning session yesterday, we know what we have to do, we know how to do it, let's get on with it. And we have a farmer just down here, if I may indulge, who has got a pilot plant. He is the general manager of Craigmore Sustainables. They have a pilot plant on one of their dairy farms. Do you want to say anything, Stu, about it? Could you give him a microphone? Yeah. Come up here. Jump up. Pleasure. Thanks, Stu.
So yeah, really easy to install. I think this is version 2, so you got all the bugs out of it. It went into play a couple of months ago. It was just basically came in and got installed. So and there's been no issues post-installation. There's possibly some other benefits that you haven't talked about. So you reduce E. coli, and you may actually reduce other bacteria or viruses. So we may see an animal health benefit in time. So you won't get the Theileria or the BVD, or possibly some of the mastitis bugs transferred between cows as well.
Right.
Yonis would be another one. So,
yep. Thanks, mate. When we approached the dairy industry and MPI and others with this technology, no one says, fantastic, what a great idea, you've done well. They say, well, the CapEx and OpEx is too much, it's never going to fly. So the professors are working on reducing the CapEx of the actual equipment and the OpEx, in other words, the cost of polyferrous sulfate. So that's where we are, Harry.
Thank you very much. And we do have time for a question. Again, Ant's been a very experienced presenter, has given us a little bit of time. So there is a time for a question, or maybe even two from Ant. So I've got one on the third row, Luke.
Yeah, I'm just wondering, do you spray this on the paddock as usual, or you've settled out a whole lot of the sediments at the bottom? How are you dealing with that, and does it affect the fertiliser benefits of spreading effluent normally?
Yep, so the prof's away here. Thanks for the question. They have already tested, in the end you have to empty your effluent pond, right? And so farmers do, and so they've tested the treated effluent in terms of pasture health and soil health and productivity, and found that it's no different from standard untreated stored effluent. So.
I have time for one more question up on the right-hand side. Thank you, Luke.
Thank you. Two questions, or two-part question. So first off, if we're putting iron into the effluent and then spreading that on the paddocks over a long period of time, are there any concerns in terms of environmental contamination? And secondly, obviously for us, effluent is a small part of our total emissions, but in other systems, like in the US, it's a much bigger proportion of their emissions. Do you have any plans to look at how this might work in a US type system?
World domination, yes. No. So Ravensdown is a New Zealand farmer-owned cooperative, and we did have aspirations to go to the world with DCD. Well, that got certainly knocked on the head pretty quickly. Our new CEO seems to have aspirations to look at opportunities around the world, so watch this space. I can't answer for him. So that's the second part of the question. The first part was about iron. As a soil scientist, I can tell you that our soils are rich in iron. We've got so much iron, we don't know what to do with it. It just stays in the soil. And so the small amount of iron that we'd be adding extra in the effluent is you wouldn't detect an increase in iron levels in soils for many years. To the Commission from Samoa, the profs and I would love to come to Samoa with an eco pond.
Even without an eco pond, we'd probably love to go to Samoa. Thank you, Ant. Very good.